Awesome. We're going to keep on going here. We should be able to complete this chemical equation here, given that this nitric acid is our acid and this sulfate ion is our base. Remember, an acid is a proton donor, and the base is our proton acceptor. All right, so on my product side, my acid is going to have lost that hydrogen to become just the nitrate ion. And since it loses that positively charged ion, it's going to be left with a negative sign. So decrease number of hydrogens by 1, decrease the charge by 1. We go over to our base. That's going to accept a proton, so I'm going to increase the number of hydrogens by 1. And since it accepted that positively charged proton, its charge is also going to increase by 1. Okay? We had fancy names for these products. Our acid becomes what we call the conjugate base. And our base becomes what we call the conjugate acid. And again, these sort of terms, conjugate acid, conjugate base, come from if you're looking at the reaction in the reverse direction. Your conjugate acid is playing the role of an acid. It's donating a proton in the reverse direction. And your conjugate base is playing the role of the base. It's the one accepting the proton in the reverse reaction. And remember, that's one of the things that we want to do in Chem 1b compared to Chem 1a is start looking at these reactions as if they're going in both directions at once, because that is what's truly happening here. Cool. All right, so where we're going to sort of pick up today is talking about a very special chemical reaction here, a very special acid-base reaction called the auto-ionization reaction. And this is an acid-base reaction between water molecules. All right, so what do I mean by that? I'm going to take two water molecules, and they're going to react with one another. One of them is going to play the role of an acid. The other one is going to play the role of a base. Okay, so everybody take a second and give me the products of this auto-ionization reaction here. Okay, so if one of these water molecules is playing the role of an acid, it's going to donate its proton, right? So I'm going to decrease my number of hydrogens and decrease my charge. Okay, this would be my conjugate base. And we have a special name for this ion here. What do we call this guy? So this is hydroxide. All right, and then my conjugate acid is going to be the result of water accepting a proton. So I'm going to increase my number of hydrogens by 1 and increase my charge by 1. So this is my conjugate acid. And we have a special name for this guy here as well. What do we call this one? So this is hydronium. So it turns out that in every sample of water that you have, there are water molecules reacting with one another in an acid-base reaction to create hydroxide and hydronium, okay? And it's always a very, very tiny fraction of water molecules. By no means am I holding a container of hydroxide and hydronium only. It's only a very small fraction of water molecules undergoing this auto-ionization reaction. But nonetheless, it's a very significant sort of reaction here. Let's take a second, and we're going to be good here. I'm going to put in my state symbols. For water that's considered a pure substance, that's going to get these liquid designations, okay? Hydroxide and hydronium, these are now ions floating around in solution, so these would be aqueous. All right, and everybody take a second and give me the equilibrium expression for this reaction here. All right, equilibrium expressions, we remember what over what? Products over reactants, okay? I'm going to do my products, my concentration of hydroxide, my concentration of hydronium, and then am I going to include those waters in my equilibrium expression? No, because remember, solids and liquids do not appear in your equilibrium expression. They're considered pure substances, only gases and aqueous compounds, right? So here's my equilibrium expression for this autoionization reaction. And just like all reactions, we can look up what that value is for our equilibrium expression. And in this case, at room temperature, the product of these two concentrations equals 10 to the negative 14. This is going to be an important value to keep in mind here. It's a little bit of a lie, but to make our lives a little bit easier, we're going to pretend that this 10 to the negative 14 is an exact value. Truthfully, there's some experimental error involved there, but we're gonna go ahead and approximate that as exact. Okay? So what's really important about this equilibrium expression here is that this is true for all aqueous solutions. In every aqueous solution, the product of your hydroxide and your hydronium concentrations will always equal that same magic number, 10 to the negative 14. Okay? So this is going to be a really important concept going forward, because essentially it means that if you know one of those values, one of those concentrations, you can always find the other one using our autoionization equation. All right? Because the product always equals that same number. So let's use this equation here. Let's say, what is the concentration of hydronium in a solution where the concentration of hydroxide is 6.78 times 10 to the negative 9 molar. Okay, everybody take our autoionization reaction, do some algebra here, and solve for my hydronium ion concentration. All right, yes, everybody punch this into your calculator. Let's make sure that we're all getting the same value here. All right, so I'm going to take my autoionization equation. I'm going to try to solve for my concentration of hydronium, meaning I need that all by itself. So I'm going to move that hydroxide concentration over by dividing both sides by that value. That'll cancel it out on my left-hand side here, leaving me with hydronium by itself, which is what I want. And then I just got to plug into my expression here that value that I was given for my hydroxide ion concentration, that 6.78 times 10 to the negative 9. All right, if I punch that into my calculator, I get 1.4749 something something times 10 to the negative 6. Okay. What would my units be on this value? Talking about concentration. What are our concentration units? That big M, molarity. And then how many sig figs should I have in this answer? I'm going to round it off to 3, so 1.47 times 10 to the negative 6 molar. Okay. If you got that same numerical 1.4749 business, but then your exponent was wrong, like I guess it would be times 10 to the negative 23, all right? The problem is order of operations. When we're dividing by a number in scientific notation, we need to keep both that 6.78 and the 10 to the negative 9 in our denominator. So you got to throw that thing in parentheses when you punch it into your calculator, all right? So if you got that same sort of numerical value out front, but your times 10 to the business was wrong, that's most likely because of the fact that you messed up order of operations by not putting that denominator in parentheses, right? In order to keep them both under that division sign, you got to throw it in parentheses here. Cool. All right, and again, the whole point being, using this auto-ionization relationship, if we know one of these values, so for example, we knew our hydroxide ion concentration, we can always find what the other one is, right? Because the product is always equal to that same number. All right, so real quick, let's talk about solutions that are classified as acidic versus neutral versus basic. Okay, it has everything to do with these concentrations that we just calculated here. An acidic solution. What it means to be acidic is that the concentration of hydronium is greater than the concentration of hydroxide. All right, a solution is considered neutral if these two are equal to one another. Hydronium ion concentration equals hydroxide ion concentration. All right, and then a solution is considered to be basic if the concentration of hydronium is less than the concentration of hydroxide. Okay, so what makes an acidic solution acidic is that there's more hydronium ions in there floating around than there are hydroxide ions. And on the flip side, what makes a solution basic, there are more hydroxide ions floating around in that solution than there are hydronium ions. That's where those terms come from. Okay, so if we look back above at our problem that we did up here, my concentration of hydroxide was 6.78 times 10 to the negative 9, and my concentration of hydronium was 1.47 times 10 to the negative 6. What would we classify this solution as, acidic or basic? What number is bigger, 10 to the negative 6 or 10 to the negative 9? 10 to the negative 6, right? So this would be an acidic solution, okay? These negative exponents, they're going to kind of play a really important role in this particular chapter. When we're talking about concentrations of these two species, they tend to be quite low, right? So negative exponents, expressing these concentrations with negative exponents is going to be really common, okay? So remember, the more negative the exponent, the smaller the number is. Those are tiny numbers. All right, and these concentrations are really important, right? Like again, this is how we classify solutions. We're going to talk a lot about the concentration of hydronium ions in a solution. Okay, that's going to be the punchline of a lot of our problems, okay? But we have this different way of measuring hydronium ion concentration that's much more ubiquitous, and that is what's called pH. Okay, I think everybody's heard of pH before. If you've ever had to maintain like a pool or a hot tub or something, you got to worry about the pH levels in there. Really what you're doing when you're adjusting those pH levels is changing the concentration of hydronium ions. That's all pH really is. It is just a stand-in for our concentration of our hydronium ions. Okay, we'll say it's proportional. Okay, it is that same piece of information just restated on what's called a log scale. Okay, so the pH of a solution is equal to the negative log of its hydronium ion concentration. So if you know the hydronium ion concentration, you can find the pH and vice versa. They're the same piece of information, just sort of restated. All right, so look, logs are something you would have been introduced to in an algebra class. I'm not going to spend a whole sort of whatever introducing to logs, but let's just talk real quick about what the heck a log is. Okay, so logs are the inverse of exponents. All right, so what do I mean by that? Multiplication and division, those are inverse operations of one another, right? What you can do by a multiplication, you can undo by a division, right? That is the relationship between logs and exponents, okay? The log of, for example, 10 squared is equal to that exponent too. That's what a log is doing. Okay? Everybody take out your calculator. You have a log button. Back in the day, this is way before my time even, they actually had this crap tabulated in these giant books to look up your log values. Now, of course, we got calculators to do it for us. Let's make sure we can find our log button real quick. And everybody's going to calculate the log of 0.001. Okay, let's make sure we can find that button, know how to use it. Okay, this is just the log of 10 to the negative 3, which would then be negative 3. All right, let's do one more here. Let's do the log of 476. All right, we get some 2.6776 business. Okay, so what does this mean? Again, this is the inverse of an exponent. So if we take 10 and we square it, or not square it, I guess, raise it to the power of 2.6776. If you actually copy and paste the number on your calculator, you will see that you get a value of, drum roll, 476. All right, you get that same number back out. Now, exponents with decimals look really, really weird. Okay, we're not really used to raising things by a fractional power here. But there is absolutely nothing illegal about it. There's nothing wrong with raising something to a power that has a decimal in it. So that's what we're going to see for our log. So that's what a log's doing for you. It's the inverse of this exponent operation. Okay? So again, point being is if we know our concentration of hydronium, we can find our pH. Okay? If we're going to flip this equation around, and this is something that y'all with bomb algebra skills would know, but let's just put it down for those of us who don't have bomb algebra skills. If we're going to reverse this equation here, our hydronium concentration would be 10 to the negative of that pH. So again, if we know hydronium ion concentration, we can always find pH and vice versa. If I'm given a pH, I can then calculate what the hydronium concentration is. These are just one in the same pieces of information, just sort of restated. Okay? So when you get to more advanced chemistry, you will sort of begin to understand why this log scale is convenient, especially when you're talking about values that range by such large orders of magnitude. All right, when we're talking about hydronium concentration, it can be as small as 10 to the negative 14 or as large as 10 squared. Huge order of magnitude difference there. A log scale just kind of makes that more convenient. Okay, and I know y'all are like, yeah, super convenient. Thanks for that. All right, but trust me, there's a reason why us scientists do it, and more importantly, that is the standard, right? That is, I think everybody's heard much more about pH than they have hydronium ion concentration, right? That's how we talk about that in chemistry. Okay, so let's go back up here. We found our hydronium ion concentration for this solution. All right, now let's restate that in terms of our pH. Okay, so everybody take a second and tell me what the pH of this solution is. And just one more thing real quick. It's the negative log of the hydronium ion concentration. Importantly, your calculator has a negative sign and a minus sign, and they are not the same thing. So make sure you use the negative button when you're doing a negative log, or you'll get a syntax error. All right, so my pH of this solution is 5.83122. Okay, we'll talk about sig figs here in a second. The units for pH, and this always kind of boggles my mind a little bit, but pH is actually a unitless quantity. We've seen this before when we were talking about mole fractions. There are no units on there. So it always makes me a little weird to have like a naked number. So I typically write pH equals, but the pH is that 5.83122 with no units on there. There's no units for pH. Okay? So for our criteria of acidic, basic, and neutral, we can sort of restate this in the world of pH. Okay? Saying that the concentration of hydronium ion is greater than hydroxide ion, this means that the pH would be less than 7. In a neutral solution, if these two are equal, and you can sort of prove this by solving it in your autoionization equation, this would mean that the pH is equal to 7. All right, and if you have a basic solution, then the pH is greater than 7. Okay, so again, we looked at our concentrations to determine that this was an acidic solution. We can convince ourselves that we get the same answer if we look at our pH, right? A pH of 5.8 means that we have an acidic solution. All right, so before I complicate things talking about sig figs. Let's just do one from scratch here. All right, I'm going to give you this solution that has a concentration of hydroxide equal to 4.6 times 10 to the negative 4, and I want to know what the pH of this solution is. Bless you. All right, everybody check with your neighbors, see if you're getting the same thing, setting it up the same way. All right, so in order to solve this problem, I need to first find my hydronium ion concentration. So I'm going to use that auto-ionization relationship. Solve it for hydronium ion concentration by dividing 10 to the negative 14 by that 4.6 times 10 to the negative 4. This leaves me with 2.17391 times 10 to the negative 11. My units are molar, okay? I'm going to mark my sig fig in this number, but I'm not going to round it off yet because I'm going to turn around and do more math with this number, right? So we don't want to round in the middle of a problem, only at the very end. So now in order to do pH, so in order to get hydronium ion concentration, I use that auto-ionization relationship. And now in order to get pH, I'm going to use the fact that pH equals the negative log of that concentration. Okay, so I'm going to let the calculator do its magic here, punch that in, and I get 10.662757. And again, this is pH, so what are my units? I don't have units for pH. Okay? All right, so in order to finish this off, we got to talk about sig figs and our log scale. Okay? Every operation has different rules for sig figs. Multiplication and division, they have a set of rules for sig figs. Addition, subtraction, they have a different set of rules for sig figs because those are different operations. We now have introduced this new operation of taking a log. So we got to introduce a new rule for sig figs for our log scale here. Okay? Our rules for sig figs and logs is that the number of sig figs in our concentration equals the number of decimal places on our log scale, i.e. our pH. So the number of sig figs in my concentration, that's going to correspond to the number of decimal places in my pH. All right, so what do I mean by that? If we go back up to this problem here, our concentration had 2 sig figs. So our pH needs to have 2 decimal places. All right, I'm going to round my pH here to 10.66. That's how I'm doing my calculations for pH to the correct number of sig figs. I got to look at the number of sig figs in the concentration. That's how many decimal places my pH should be reported to. Okay, so again, new operation, new rule. Here is our rule for sig figs and logs. All right, so everybody take a second and go back up to that very first problem that we did and report that pH to the correct number of sig figs. All right, so my concentration had 3 sig figs, which means that my pH needs to be rounded to 3 decimal places. So final answer reported to the correct number of sig figs is 5.831. Okay, the number of sig figs in your concentration correspond to the number of decimal places in your pH. All right, so let's go back to our auto-ionization relationship. I guess real quick, let's annotate this. This K value here, it gets a special little subscript because it's corresponding to this auto-ionization reaction in water. This would be the KW is what you'll see symbolically to represent that 10 to the negative 14 value. All right, so we're going to take this relationship here, our KW expression, and we're going to do some algebra to it. right? Remember, in algebra, we can do anything we want as long as we do it to both sides of our equation here. So what I'm going to do is I'm going to take the negative log of both sides of this equation. Okay? If we look on the left side, we have this multiplication problem inside our log. All right, I had a math professor that always said, in the magical world of logarithms, this multiplication will become an addition problem. So what do I mean by that? It turns out that the negative log of these two multiplied together is equal to the negative log of each one added together. All right, again, log algebra is kind of weird. You might remember going over this. You're just going to trust me, okay? All right, and so we can simplify this expression here because what do we have a new term, fancy term for the negative log of the hydronium concentration. What is that? What is the negative log of the concentration of hydronium? The pH, exactly. Okay, and this negative log of 10 to the negative 14, that's just a number, right? So let's punch that into our calculator. Somebody tell me what the negative log of 10 to the negative 14 is. Positive 14, exactly. Okay, so we're going to define this new quantity here, the negative log of our concentration of hydroxide. We're going to call our POH. Okay, hydronium is pH, hydroxide is POH. And now we just have this restatement of our autoionization relationship that we can use in our problems. You can actually approach these problems in two different ways. So now we're going to do another one using this autoionization relationship stated on the log scale here. Our pH equals plus POH equals 14. Okay, so what is the pH of a solution where the concentration of hydroxide is 4.732 times 10 to the negative 12 molar? Okay? And what we're going to do is you're going to first calculate the POH and then use that in our restated autoionization relationship to get the pH. Okay, so everybody take a second and see if you can't solve this problem here. So in order to get the POH, I'm going to take the negative log of that concentration, because that was the hydroxide concentration. So I get 11.324955. What are my units? Trick question, right? No units for our pH or POH. Okay. What about sig figs? What number am I going to mark in my POH? How many sig figs are in my concentration? 4 sig figs. And that corresponds to the number of decimal places in my POH. So I need 4 decimal places. All right, so I'm going to mark all the way down at that 9 there. I'm going to go on and do more math with this number, so I'm not going to round it off quite yet. In order to get my pH, I'm going to use my auto-ionization relationship. pH plus POH equals 14. Okay, how would I rearrange this to solve for pH? Subtract that POH from both sides, right? This is an addition problem, so I'm going to do the reverse, which is subtraction. So my pH is going to equal 14 minus my POH. Okay, and just like before, we say that that 14 came from that 10 to the negative 14 is exact. So this would leave me with a pH of 2.6750, 2.6750, 44, but my sig figs are again those 4 decimal places. So final answer, 2.6750. Is this solution acidic or basic? Acidic, right? I got that low pH value lower than 7. You can convince yourself by calculating concentrations as well, but again. So this is the same problem that we did before, just approached in a slightly different way, where we use this restatement of our auto-ionization relationship as opposed to the product of the concentrations. Either one of those approaches will give you the same answer. Okay? Whichever one you pick is your favorite, go for it, all right? People tend to like the POH plus pH route. It's equivalent. You can do either way, all right? So whichever one you favor, go for it. All right, so now we're going to try to start thinking more practically here. We talked a lot about acids and classifying acids at the beginning. So if I'm given a solution of, say, hydrochloric acid, how do I figure out what the pH of that solution is? Okay? And we said it's going to be a lot easier for strong acids than it is for weak acids. So that's where we're going to start here. Calculating the pH of a solution of strong acid. All right, so I'm going to put down a strong acid here. Let's just take, for example, nitric acid. Okay, and I want to see if you guys can remember what our Ka equation is for this reaction here. When we're talking about making a solution of an acid, we're always talking about a very specific chemical equation here. See if you can't remember what that was. Right? We called these our Ka equations. To make a solution, I'm going to take this nitric acid, this HNO3, and I'm going to put it in what? Water. So that's what we're talking about, is the reaction between our acid and water here. These are our Ka expressions. I'm going to be good with my subscripts here. All right, so everybody take a second and give me the products of this reaction. To be clear, the nitric acid is playing the role of the acid, which means that water is going to be playing the role of the base. All right, so my nitric acid loses its proton. It becomes the nitrate ion. And water, when it's playing the role of a base and it accepts that proton, it becomes hydronium. And what the heck have we just spent a whole boatload of time talking about? That hydronium concentration, right? Okay, so let's take a look at a problem here. What is the pH of a solution where the concentration of that nitric acid is 0.049 molar? Okay, so we're trying to figure out what the concentration of this solution is going to be here. I know the concentrate, it was prepared so that my nitric acid concentration is 0.049 molar. All right. Now we're going to have to use something that we learned about our strong acids. What did it mean to be a strong acid? That this particular reaction did what? Favors the products, and not only favors the products, right, but very strongly favors the products. So much so that we can say that this reaction goes 100% to completion, right? So that means 100% of these HNO3 molecules become our hydronium ion. So for strong acids, because this reaction so strongly favors the products, we can just go ahead and say that our initial concentration of our hydronium, or of our acid, our strong acid, is going to equal the concentration of hydronium at equilibrium. All right, so this solution was prepared to 0.049 molar nitric acid. Well, 100% of those nitric acid molecules have turned into hydronium molecules. Yeah?
It might not be related to that, but the arrows for the equation, I thought a strong acid would be like a single arrow showing it's like 100% dissociated, and the arrows going back and forth would be equilibrium, so like for the weaker acids. So is this a weak acid or strong?
No, so two things. When we are thinking about equilibrium, you can always, for every reaction, because they will all technically reach equilibrium, you can always get away with this double-headed arrow here, okay? And since we want to be thinking, we're sort of building to a point where we want to be thinking about the equilibrium expression for these Kas. That's kind of how I wrote it, okay? But you could absolutely 100% be correct to just put a one-headed arrow on there because, yes, this reaction very strongly favors the product side. So one is not necessarily incorrect and the other one correct. It kind of depends on the context in which you're thinking about it. And I want us to start to think about these acid-base equations as equilibrium expressions. We're going to see for weak acids that's really, really important. But yes, you could be even more descriptive by putting a one-headed arrow to show that it very strongly favors the products. Does that make sense? Cool. All right, either way. Okay, so the point being is that our concentration of hydronium is 0.049 molar, right? Because it's a strong acid, I can just say very simply that the concentration that I prepared my strong acid to, that's going to equal my concentration of hydronium at equilibrium. Okay? So everybody take a second and tell me what my pH is here. All right, so I'm going to take the negative log of that 0.049. I get 1.30980. All right, and where am I going to round this off? To sig figs. So I need 2 decimal places in my pH. So 1.31 is going to be the pH of this solution. All right, is it acidic or basic? Acidic. And does that make sense? Because we added a strong acid to this solution? Check, check, right? So indeed, we got an acidic solution. Okay. So again, our sort of trick here that we're going to use, and again, it's going to make our pH for strong acid problems much easier, is because these reactions go 100% to completion here. We can say that our concentration of our strong acid is equal to the concentration of the hydronium ions when it reaches equilibrium. Which happens almost instantaneously for these acid-base reactions. They go to equilibrium like that. Okay. So we talked about strong acids. Let's take a second and talk about strong bases. Okay, so how do we spy a strong base? Remember, for strong acids, we had to remember that list of 6. That's how we spy a strong acid, is if it's part of that list. Strong bases are a little bit easier. These are just any sort of soluble ionic compound that contains a hydroxide ion. And what does it mean to be ionic? Right? If I'm looking at the periodic table, how can I tell that I have an ionic compound? Metals and nonmetals, right? So in particular, your cation is going to be a metal here. So for example, sodium hydroxide, right? I have that sodium metal in there, that hydroxide compound, so I know that this compound would be a strong base. All right, that OH is the giveaway here. All right, and then like strong acids, what makes a strong base is that it 100% dissociates in solution. So if I take my sodium hydroxide. You can buy this as a solid. You put it into water, it's going to 100% dissociate into sodium ions, and they don't do a dang thing but float around in solution, and hydroxide ions, which are our base. All right, so like a strong acid, this reaction goes 100% to completion. Okay, so if we're going to try to calculate the pH of a solution of strong base, we get to use a very similar kind of simplifying assumption here, and that is that the concentration of that strong base is simply going to equal the concentration of hydroxide when it very quickly reaches equilibrium. All right, so keeping this in mind here, what can we do? I'm going to give you a problem. I want to know what is the pH of a solution where the concentration of sodium hydroxide is 0.00253 molar. All right, so I'm going to take the negative log of that number in my problem. And then I'm done, right? No, if I take the negative log of that number, what have I just solved for? The pOH, right? I still don't have my pH, so be very careful. Everybody thinks pH problems, they automatically start taking negative logs of every number they see, and they're like, all right, I'm done. Make sure that, similar to what we talked about in our equilibrium problems, make sure to refer back to what quantity it is that we're talking about. If I take the negative log of a concentration of hydroxide, I am talking about a pOH. So that's a great first step, but I'm not done then. All right, so if I punch this into my calculator, 2.59. Okay, that's my pOH. All right, in order to find my pH, I then have to use the fact my auto-ionization relationship tells me pH plus pOH equals 14. So if I rearrange this, I can get my pH equals 14 minus that pOH. Actually, before I move on, I'm going to be good and mark my sig fig here. This has 3 sig figs, so that's going to correspond to 3 decimal places. All right, so then 14 minus that number gives me a syntax error. So clearly I didn't do something right. There we go. Equals 11.403120. Okay, with my 3 decimal places, 11.403. Is this solution acidic or basic? Basic, right? Which checks out because I prepared my solution with a strong base. So absolutely, I get a basic solution here. Okay? So for both strong acids and strong bases, the key is that we get to assume because it's strong that 100% of that compound will dissociate in solution. Right? So for a strong acid, that means that the concentration of strong acid equals my hydronium ion concentration, so I can find my pH that way. If we're talking about a strong base, that means that the concentration of base is equal to my hydroxide ion concentration. And I can find my pH that way by using my auto-ionization relationship.